Now let's make sure that we know how to read computer output when it's given to us, say on a final exam or something like that. Hint, 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 hint. So suppose researchers wanted to know whether the use of cell phones impairs reaction times in a driving skill test. Reaction times are measured when subjects perform the driving task without using cell phones, that's sample 1, and then again with the same subject using the cell phones, that's sample 2. Before observations were taken for these two conditions, subjects had a warm-up time interval to become familiar with the task, so reaction times would not tend to change from one condition to the other merely because of increased formality. So here are the hypothesis test outputs for two computer programs. Now, how many people were sampled? Well, you can see that right here. It's 32 for Minitab. Now, StatCrunch doesn't give it to you straight up. They tell you the degrees of freedom right there is 31. So if you know degrees of freedom is 31, then you can suppose that n must have been 32. And remember, you don't know which computer output you're going to get on an exam, so you want to make sure you can find everything with both outputs. All right, so 32. So the degrees of freedom is 31. Now, what was the average time when not using the cell phone? Well, Minitab's really nice because it says right here, not using cell, right there. I can't really ask that question of you, I'm going to be honest, because StatCrunch isn't giving us enough information to figure that out. So if I do ask that kind of question, I must be giving you Minitab output. The standard deviation is 66.4, and again, StatCrunch doesn't give that, only Minitab does. So if I'm going to ask you that kind of question, it has to be from Minitab. That said, for the next two, E and F, that I could do from StatCrunch or Minitab. The average time difference is down here, negative 50.63, or here, negative 50.63 right there for the sample difference. And then the standard deviation is 52.49, right there, 52.49. 52, oh, they don't give it to you. Oh, they give you standard error. Oh, so don't forget, hold on, let me pause. There we go. So you could use that formula for standard error, which is right there. S over the square root of n, which is, hold on one sec. There we go. So standard error is S over the square root of n, which is S over the square root of 32, which is equal to 9.278. You can just find what the square root of 32 is and multiply both sides of the equation by that, and you've got it. So you should be able to find 52.49 for either problem. And I don't know if Minitab, yeah, Minitab also gives you the standard error, 9.28. See it right there? So that's the S over the square root of n part, and the standard deviation is just the S part. All right, now the problem states that suppose researchers wanted to know whether the use of cell phones impairs reaction time in a driving skill test. Which one of those is this? All right, so it's the middle one, but let me explain why. Because it said that we was doing not using cell minus using cell. Now let's think about this. If you're driving, if your reaction time is impaired, that means that when you're using the cell, it's going to take you longer than when you're not using the cell. So when you're not using your cell phone, can you imagine like a driving thing? When you're not using your cell phone, it should be smaller than when you use your cell phone. That's why when you take the difference, you should be getting a negative number, okay, less than 0. And I showed you the difference part right here for part H. So the computer outputs use this. They say the difference like that. Right here, you can say difference not using cell minus using cell, not using cell minus using cell. You can see the null and alternative up there, mu1 minus mu2. That's okay. It's the same thing that we're doing up here that I've boxed in red. It's just that the difference, mu d, is that subtraction. And I showed that right here. Not using should be less than using, right? So when you use your cell phone, it should take you longer than when you don't use your cell phone. So not using should be less than using. That means mu1 should be less than mu2. If you subtracted mu2, that would be mu1 minus mu2 is less than 0, and that would mean the difference is less than 0. That's why I've boxed this red one up here. Okay? So it's totally fine that they just use the subtraction symbol instead of the d's. It's the same thing. All right? But what if we reversed the groups? What if I said it was using cell minus not using cell? Well, that would just cause it to flip-flop, right? So using would be in front, but it would be a greater than, right? Because if you looked at this part right here, not using is less than using. We think that using should be greater, right? It should take you longer to do something when you're using your cell phone because you're distracted. So using greater than not using, that means mu1 is greater than mu2. So when you subtract them, it should be greater than 0. So the difference should be greater than 0. All right. Now what about the test statistic? Well, that's negative 5.46 right there, and negative 5.46, easy to spot. Now the p-value is the next thing it's going to ask. You can see StatCrunch says it's less than 0.0001. Minitab's a little worse about this. It says it's 0, which of course it isn't really 0. It's just rounding it, right? So it's really, really small. That much you do know. So if you want to say it's 0, or if you want to say it's less than 0.001, whatever. It means it's very tiny. Okay, so now we got to do step 4. So you draw a normal curve. You're going to have to make it go out pretty far because your test statistic is at negative 5. Negative 5.5, honestly. So you got to go out to 5 standard deviations from the mean, which is really far way out here to the left. And the p-value for that is really small, less than 0.0001. So you draw a curve, a t-curve. You extend it out a ways on the left here to get that test statistic in there. All right, so would that be significant? Oh yeah, very much so, right? Because if you have a p-value that's that low, that is totally less than 0.05. So we reject the null hypothesis. And remember, rejecting the null is what is statistically significant, right? Leaving the null in place is not significant to us. We assumed the null was true, so that wouldn't matter to us at all. And if we reject the null, that means there is enough evidence to support the claim that using the cell phones is impairing reaction time. All right, we're done with that portion. Now let's see about the confidence interval. All right, now confidence intervals are just like before, and honestly this one's a pretty simple one. It's just you're using it for the difference, not for the individuals, right? So back to our touch therapy data, which we've already worked with before, we could make a confidence interval for those differences. Now the formula for it says we need d bar plus or minus t alpha over 2 SD. Well, we found a lot of this stuff already. We found d bar to be negative, oops, not a fraction, negative 1.923. Then we need plus or minus, oopsie. I can't remember the there it is. Okay, T I'll figure out in a second. SD we found to be 1.605. Square root of N is square root of 13 because that's the touch therapy, not the cell phone. That's the one we used before. Now T. Don't forget that our degrees of freedom for this thing was 13. Oh, excuse me, was 12 because we had 13 patients altogether. So degrees of freedom was 12 right there. So it's probably simplest just to go to the table. Go to 12 degrees of freedom. Now keep in mind this was a, what kind of interval? 95? Let's look. 95. Okay, so 95% confidence interval, so we want to go to the 0.025 column. So 0.025, because remember that's how much is in each tail. 95 makes the middle, 0.025 on the left, 0.025 on the right to make 1 for the whole curve. And you grab 12 degrees of freedom right there, so it's 2.179. Oopsie, we put it right there, 2.179. All right. So that's that. Now, we could just type this into a calculator. I mean, it's actually not even that hard a problem. Just a reminder, df is equal to 12. Alpha was equal to 0.05. So alpha over 2 is equal to 0.025, just as a refresher. Okay. There we go. Okay, so you could type this in, or we could use StatCrunch. Let's do that, shall we? Now notice we already found these differences. They're the stuff we were working with before. But you can do it you can do it a couple ways. You could go to T statistics, one sample with data, and you could say, hey, we've got these differences. Next, make a confidence interval. There it is, calculate. Or we can go T statistics paired, right? Say, okay, our beginning was in the after, our group 1 was the after, our group 2 was before. And of course that was kind of reversible, but that's how we set up this problem. So after, before, click next. You want a confidence interval, 0.95, calculate. There it is as well. So it's kind of whichever way you want to think of it. The output will look tiny bit differently. Here, I'll show you. I'll actually paste this right in here. So this is examples 1 and what is this one? 5 and 5. Okay, so you can see right here it tells you it's the difference, so that's kind of nice. When you do the other one, when you just have the differences already ahead of time, it doesn't tell you it's a subtraction new problem. You still get the same numbers, but it's not a subtraction because it didn't know that it was a difference when you did it. So in a way, the paired one's a little bit nicer because it's giving you a little bit more info. And there you go. You can see the numbers, negative 2.89 to negative 0.95. So that's what you write down. I'll write it right here. Negative 2. What was that again? Come back. There it is. 2.893. There we go. 2.893, comma, negative 0.953. And there you go. That's your confidence interval. Done. And of course, you didn't really need StatCrunch, but isn't it a lot easier when you use it? Oh, yes. All right, so what's the margin of error there? Well, recall that the margin of error is the distance between the outer edge and the middle. So upper minus the middle, which is, or the point estimate, right? That's what the middle is called, point estimate. So that would be negative 0.953 minus a negative 1.923, which is equal to 0.97. You could also do it middle minus lower if you wanted, which would be negative 1.923 minus a negative 2.893, like that. So whichever way you want to find it, but you should be finding 0.97. That's your lovely margin of error. It's the distance, if you recall, from the edges to that center. All right, now interpret the confidence interval. We are, oh, let me pause you. I'll be right back and type this up. All right, we are 95% confident that the pain levels were lowered by between, and again, the negative part didn't really matter. The negative was just because of the way we set up the differences to be after minus before. If you had done before minus after, these would have ended up being positive, right? So you can kind of ignore for the interpretation part the negatives and just say, we think the pain levels were lowered between 0.953 and 2.893 on the pain scale. It was some kind of numeric pain scale they were talking about. Usually when you go into the doctors, they say, you know, where's your pain level at 1 to 10, that kind of thing. All right, so we're 95% confidence we lowered the pain levels about that much. Is that significant? Absolutely, it's significant. If you're lowering your pain levels of your patients by around 1 to around 3, that's a good thing, right? You want your patients to be in less pain. So that would imply, because 0 is not in that interval, 0 is nowhere between 0.95 and 2.89, that would imply that there is a significant difference before and after the touch therapy and pain levels. Now remember, we learned before that 0 is kind of the thing, because if they weren't really different from each other, then 0 would be in the interval, remember? From back here when we set up those null hypotheses. If they're not really different, then their difference will be around 0. But you just found the confidence interval for that difference, and it's nowhere close to around 0 because 0 is not in the interval, right? If they weren't different, there it is, then subtracting them would be around 0, and it isn't. It's nowhere close to 0. 0 is not contained in that interval, therefore you are showing a big difference. All right, now what about name brand versus store brand merchandise? So I have computer programs conducting a confidence interval for the difference between name brand price and store brand price. You can see the confidence intervals, negative 2.37 to 0.771. Poof, there I highlighted them so you could see it. Does it appear that there's a big difference between them? And the answer is no, right? It doesn't appear like that at all because 0 is contained in that interval. Therefore, there's not a significant difference between name brand and store brand prices. And of course, I could ask you a whole bunch of other questions like how many name brand items did they pick? What was the average price? 3.14. What was the standard deviation? 1.12, and so on. So all of those questions are still fair game, and I could ask them to varying degrees from these two computer outputs. All right? Okay, we're done with section 11.2. I'll see you back here for the more difficult 11.3 when everything's independent. Much worse, much harder. See you then.